Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, today video session we're going to solve problem from handout number 8. So to be more specific, the topic of the discussion will be focused on, as shown here, conductor free space boundary conditions. Since we have learned about a new material after conductor, which is known as dielectric, we can replace the word free space now to make it more general by stating conductor dielectric boundary conditions. Okay, so to make it more general, so this should be the topic of interest for in this particular video session. So inshallah we're going to solve together problem shown here, which are problem number 15, 16 and 17. Okay, so that should be our problem that we're going to focus on. Problem number 15, number 16 and number 17. So okay, so this is the one that we're going to focus on. Okay, let's do problem number 15 now. So we're going to read the problem together. So region Y smaller than 0 consists of a perfect conductor. Okay, so we have a medium first been introduced in this problem, perfect conductor. Okay, while the region Y is greater than 0 is a dielectric medium. So we can see there is a boundary dividing the perfect conductor region with the dielectric medium, and the boundary having equation y equal to 0. So that is the equation of the boundary separating these two mediums. Okay, and then for the dielectric medium, since we know dielectric medium have important parameter or properties, we call it to be dielectric constant. So given here epsilon r equal to 2, and we know that this is known as either dielectric constant or relative permittivity. Then it's mentioned here, if there is a surface charge. So from the statement here, since given the unit here nanocoulomb per meter squared, so we know that the surface charge here is being represented as surface charge density. Okay, so this surface charge density located where? At the boundary. Okay, the question wants us to determine E and D at 2 points, 1 point A, 3 minus 2, 2, and B minus 4, 1, 5. That should be what we need to solve now. Okay, number 15 here. So I'm going to draw just a line presenting my boundary. Okay, so I'm going to say now my line here, let's make it to be like this. Okay, so for the region Y greater than 0, I'm going to choose the region above the boundary, and for Y smaller than 0, I'm going to state it to be the region below the boundary, and Y equal to 0 going to be the equation of the boundary. So which region is containing the conductor medium? So as stated in the question, the region where Y smaller than 0. So this should be our conductor. Okay, and the above region should represent our dielectric. And for dielectric, the value that given by the question is epsilon r, and is equal to 2. So this epsilon r is important parameter, especially when we are dealing with dielectric material. So then the next information given by the problem is state that at the boundary contain surface charge rho s, which is positive in this case, equal to what value here? 2 nanocoulomb per meter squared. 2 nanocoulomb per meter squared. So the question wants us to find what should be the value of E and D. So E representing what? Electric field intensity, and another field being asked by the question, D, representing electric field density at location number 1. Stated here a point A, 3 minus 2 and 2, and a point for the second point B given as minus 4, 1 and 5. Okay, that should be the information that given by the question. So now let's recall what we have learned before, especially regarding the issue pertaining conductor free space or conductor dielectric boundary condition. So let's recall that. So we know that when we have this particular scenario, the field at the boundary will only be in the region of good dielectric or free space. There's going to be no electric field in the region of conductor. So this reason has been explained in our lecture. So therefore we know that in this particular region, conductor, the E and D must equal to 0. Okay, that should be the first characteristic that must be able to notice in this particular problem. We must know that in conductor medium, there's going to be no electric field, or the net electric field is stated to be equal to 0. Therefore, we're going to state here the electric field of E and D in the conductor region will be equal to 0. So between point A and point B, which one should be exist in the medium conductor? So to do that, I'm going to focus on the Y value, because I know that for the Y component, to be in the conductor must be smaller than 0. So I can see from this particular information, A having Y variable equal to -2, so I know that the A point will have this type of field behavior. So I'm going to state now, for this particular position, okay, the E and D will be equal to 0. So that should be our solutions regarding for point A, due to the reason that has been explained before, where we know that in a conductor, the net electric field will be equal to 0. So now let's focus on the other characteristic of conductor dielectric boundary condition. So we know that there's going to be field in the dielectric region, and the field must behave what to the boundary. So let's remember what should be the pattern of the field emitted or exists at the boundary. Good, some of you do able to answer it. The field must be normal to the boundary. So now I'm going to draw a field normal. So that should be my field. So normal to the boundary. So 90 degrees to the boundary, because that is the second pattern or characteristic of the field at the conductor dielectric boundary condition. The first characteristic, as stated before, there's going to be no net electric field in the conductor. So we have concluded that. The second behavior of the field must be in the region of dielectric, good, and the field must always be normal to the boundary. Okay, so therefore the field must be normal. So we know that the direction of the field, okay, so we're going to the direction of the field will be in which direction? That's good. Going to be in y directions because normal to y equal to 0. So the unit vector normal to y equal to 0 going to be in y directions. How about the magnitude of the D stated in our discussion before of the D? Good. And then the magnitude of the D must be equal to rho S. Okay, that should be our D field. Where? In the region, which is in this case in the dielectric. So we know the dielectric must make an angle 90 degree to the boundary, and then the magnitude of the electric field density must be equal to rho S. Okay, so at point B, what we can conclude, the D should be equal to 2 times 10 to power negative 9 nano, and then which direction? Y directions, coulomb per meter squared. That should be the answer for the electric field density in this region, and to be more precise at the position of -415, because we can see 1, which is the value of y of point B, is greater than 0. So that should be indicating or indicator to us that point B located in the dielectric region, because the B is great. the B of y variable is greater than 0. So therefore, I'm going to state the D at point B going to be equal to 2 times 10 to minus 9 in y direction, unit wise coulomb per meter squared. How about the E? Okay, for the E, we know that D is known as epsilon E. Remember the equation that we derived in the previous lecture? And the epsilon can be represented by epsilon naught, epsilon R multiplied with the E. So therefore, to answer the question now, the D should be, the E, okay, electric field should be equal to 2 times 10 to power negative 9 divide with, because epsilon R is equal to 2, so 2 epsilon naught in y direction, so unit should be volt per meter. That should be the solution for the electric field intensity at position B. Okay, so therefore we have answered the question number 15, and as you can see, the important things that we need to know regarding question number 15, the characteristic of the field of electrostatic field located at the boundary of conductor dielectric, which as I'm going to restate again, the field in the conductor will be equal to 0. Whatever field appear to be at that particular situation only in the medium of dielectric, and that electric field density must be normal to the boundary, and the magnitude of the D must equal to the surface charge density located at the boundary. Okay, so with that, alhamdulillah, we have completed problem number 15. Okay, let's continue now to problem number 16 now. Okay, number 16 now. Okay, you can freeze the video if you want to read the question. Okay, but anyhow, I'm going to read loudly now the question number 16. Okay, it is found that the E equal to 60 x direction plus 20 y direction minus 30 z direction millivolt per meter at a particular point on the interface between air and conducting surface. So it's stated here. So the E now appear to be at a point on the interface between air and conducting surface. Find D and rho S at that point. Okay, so now number 17. Sorry, number 16. Okay, sorry about my numbering, not focus enough this today, maybe due to old age here. Okay, so given here, stated E, electric field intensity, equal to 60 in X direction, plus 20 in Y directions, minus 30 in Z directions, so millivolt per meter. So milli means that times 10 to negative 3. So this located where? At the boundary between conductor and air. So therefore, it's clearly stated that this is a boundary condition is shown now, because mentioned here, the field appear to be at a point on the boundary between conductor and air. Okay, so therefore, then the question asks us to do what? Find D and E. So find D and rho S. That's the information asked by the question. So how we solve this problem? Again, since we are dealing with this scenario, I'm going to draw general interface now. So let's say this is the interface. So I'm going to state now the region at the bottom here representing conductor, and the region up here representing air now. It's no more it's air. So air for us should be epsilon naught, the permittivity. So the E, how are we going to draw the E here? How the E should be appear in our model? Good. The E must be in which region? Yes, air. The E will not be in the conductor, because we know in conductor the net electric field will be equal to 0. So we know the E must be in the air region. That's done. How about the direction of the E? That's good. It should be normal to the boundary. So now we're going to draw the direction of the E going to be 90 degrees to the interface. So that should be our D or our E. So let's make it as D. That's what we have explained in the lecture. Okay, so the D, so going to be in this particular configuration, and we know the D should be equal to epsilon naught multiplied with E. Why? Because air. For the air, the epsilon must be represented with epsilon naught. So therefore, D equal to epsilon naught E. As what we shown up here, because dielectric should be epsilon E, and the epsilon must be equal to epsilon naught multiplied with the dielectric constant or relative permittivity. But for the air, epsilon R is equal to 1. Therefore, it's going to be noted as this equation. So how to find the D? Just multiply everything here with epsilon naught. Okay, so that's done. So, and the second question asked, so we complete this, answered the D already. How about the rho S? So the rho S should be the magnitude, and rho S should be equal to the magnitude of the D. That should be how we define rho S, the magnitude of D. And how to determine the magnitude? Simply do as what we have done in handout number 1 when we learn about vector. Should be what? 60 epsilon naught times 10 to minus 3 squared. That should be the X component of the D, correct? Plus 20 epsilon naught times 10 to minus 3 squared. That should be the Y component. And finally should be plus negative 30 epsilon naught times 10 to the minus 3 squared. So that should be our rho S. And remember to write the unit as coulomb per meter squared. Okay, so that's how we answer for the question number 16. Still utilizing the characteristic of the field at the boundary of conductor, dielectric or conductor free space. Okay, let's do the last question of regarding this issue, And that will be question number 17. Let's do question number 17 now. Okay, number 17 now. Let's focus on question number 17. Okay, number 17. A bit longer than above questions. Okay, given the potential field, so now you have a field of V. So 100 bracket x squared minus y squared, and the unit is volt. And a point P, value-wise 2 minus 1, 3, that is stipulated, meaning that is located to lie on a conductor free space boundary. So meaning the point P located where? On the boundary of conductor free space. Then the question asks us to find V. V is potential. E, electric field intensity. D, electric field density. Rho S, surface charge density. And P, polarization vector. And also write the equation of the conductor surface. So that should be what the question asks us to do. A lot of parameters need to be solved here. Okay, number 17 now. Sorry about the zoom of my handphone. Old handphone have problem zooming sometimes. Hope it's okay now. Okay, I'm going to draw my boundary to be in general shape because I'm going to assume like that. Okay, so I'm going to assume the left region is a conductor and the right region going to be air. Okay, so that's the way I'm going to represent the boundary. Not straight, flat anymore, just any shape will do. Okay, and then state by the question a point P. I'm going to draw a point P, so located at the interface. So the point P given as 2 minus 1, 3. We stated located at the interface between conductor and air. So therefore, put it there on the interface itself, on the boundary itself. So given the potential V equal to 100, so now V equal to 100, so that is the general potential field, x squared minus y squared, and then the unit here is volt. Okay, that should be the information given. So now, first, question asks us to be find V at P. Okay, that should be the first thing asked by the question. It's very simple. So what should be the potential at point P? Good. We just substitute x with what? 2. Y with what? Negative 1. So therefore, to answer this simple question, V should be equal to 100. And then 2 power of 2 minus minus 1 power of 2, and then the answer will be equal to 3. Is it correct? 4 minus 1, 3, so 300 volts. Okay, that should be the solution for the first thing asked by the question. Find the V. Subhanallah, so easy sometimes when you look into the question. But yet, students feel a bit uncertain because why? Maybe the name of EMT. Actually, it's very simple. If you feel confident on yourself, inshallah, you feel confident when you arrive at the end of the semester, hopefully. Okay, for number 2, what the question asks us to do, number 2, find E. Okay, find E. So now we have to ask ourselves. Now, because we are dealing with medium now, the E should be in which region? Should E be in the conductor? No. because we know in the conductor electric field will be equal to 0, correct? But the E stated here will be in the air region. Okay, the E will be in the air region. So how we determine the E here? Because there's no information regarding the charge. Because to find E using Coulomb's law or Gauss' law, we need to use the information of charge distribution. But in this problem, none whatsoever been given regarding the charge distributions. But yet we know given in the question is the potential. So how be able to determine the electric field from the potential? Anyone still remember the method that we can use finding E from the potential? Good. Okay, I'm going to state now, using the equation grad V equal to negative E. Okay, that should be the way we'll be able to find electric field from the information of potential. We have done this, we have seen this equation being explained, so we need to use it here. So what should be grad V equal to? Okay, so we have to use table. And then which coordinate that we need to use in order to represent the grad V equation? Because the parameter given so far only dealing with x, y, z. So we're going to state now the grad also need to be represented by the Cartesian coordinate equation. So we call that equation, state that for gradient x dv over dx. Yeah? Remember that equation that we saw before of gradient dv over dy. For Cartesian, finally z should be dv over dz. Okay, so now how we find the E? Okay, so we have to solve the mathematics first. So when we solve the mathematics, x direction still there, then substitute the V into this region, into this position. So then we have to differentiate with the x. What we're going to be the solution here should be 200x, correct? That should be the x component of the mathematics. We have to differentiate the part, so the y will become 0 because y is going to behave as a constant in this term. Okay, then we continue with the second substitution of V here. So now it's going to be minus, again, y directions, 200y. Okay, that should be the general equation of the E after differentiation. But the question asks us, what should be the E at the point P? So E, remember, must be negative of the grad. So this equation, what we solve here is this term. So the E must be the negative of this term. Should be x now. What should be the value of x? 2. So 2 should be equal to negative 400 x directions, correct? Because you have put negative, the term negative here, negative, and then put x equal to 2. 2 multiplied with 200 becoming 400, the negative is there. And then how about the y? So negative and negative, because the p is negative 1, should be positive, correct? And then you have to put negative there. So negative 200y. Then unit should be, what is it? Volt per meter. That should be the solution of our mathematics. Is it correct or should be plus? Because we differentiate negative, because we have negative here, we differentiate negative here, okay, it should be plus then. Because we are substituting y with negative 1, correct? So negative 1 multiplied with the negative becoming plus. But this is much better, this one. Okay, done already. So see how easy the questions. Okay, so we have concluded for the second part. Now I'm going to continue now with the third part of the question. So number 3 here. So find what the question asks to do, find D. And we know the D, again, only appear in the region of the air, and then the D will be just equal to epsilon naught multiplied with the E, because air due to medium is air. Okay, that should be our solution. So just multiply the E that we obtained here with epsilon naught to get our D. So that's done as well. Okay, let's continue. Okay, for number 4, what the question wants us to do, find rho S. So now, what should be our rho S located here? So meaning the rho S must be surface charge density appear at the boundary. Okay, so easy, should be equal to the magnitude of our D. So should be equal to square root of minus 400 epsilon naught square plus 200 epsilon naught square unit coulomb per meter square. Okay, so that's done. Number 5, find P. Remember, P representing what? I'm going to write here polarization vector. So how we determine the P from our previous discussions? Okay, the P actually equal to, you can use two equations. One equation is electric susceptibility multiplied with epsilon naught multiplied with the E. There's one equation that we can use, or we can use that P equal to D multiply with minus epsilon naught multiply with E. Okay, so you can use two equations to find the P, and we know that what is electric susceptibility here is equal to epsilon R minus 1. Okay, that should be how we define electric susceptibility. Relative permittivity minus 1 is our electric susceptibility. And for air, what is our epsilon R? Yes, 1. So 1 minus 1 is 0. Therefore, P in the region of air will be equal to 0. Even when you look into this equation, the same. Because D equal to epsilon naught E, when you shift this epsilon naught to the left, so it's becoming 0. So therefore, from equation number 2 also is going to be equal to 0. Okay, good. Okay, the last question before we're going to end our video session of tutorial here. Okay, and write the equation of the conductor surface. Okay, we already state this particular interface as our conductor surface. And then we know that the V field and then the potential on any point on this particular conductor must be equal to 1. Must be constant, correct? Because for a conductor must obey equilibrium properties. That's what we state in our previous discussion regarding conductor under static conditions. So we already determined at point P, the potential is equal to 300. Therefore, any point on this particular boundary or interface will be having the same value of potential, which is 300. And then we know the general equation of the V is given by such equation. Therefore, we can state now the equation of the boundary. Okay. Simply, the general equation of the V, x squared minus y squared should be equal to what value we already determined here? 300. Okay, so to simplify the equation of the boundary, now what we can state as x squared minus y squared should be equal to 3. So that should be the equation of our boundary interface. Okay, Alhamdulillah, so we have completed 3 questions easily within the short video session today. So I'm hoping that you will do as many examples as possible. The more example you do, the more thing that you're going to clarify on the thing that not sure to you. Without doing example, it's not learning EMT, actually making your life miserable, because you're going to have a tough time during the test session, and especially the final exam session. So anyway, I'm sure most of you good students want to gain knowledge to become a qualified engineer when you work later on. So therefore, you need knowledge as the tools in order to guide you to be a professional engineer. So with that, I'd like to say thank you very much. Inshallah, we're going to see each other in other tutorial session. With that, Assalamu alaikum wa rahmatullahi wa barakatuh.